Yeah, I'm John Lockman, and yeah, you may have heard me on the podcast, also on the Facts, Fiction, and Fun, talking about AI. Um, Been a long time working in artificial intelligence, quite a few years in high performance computing, more towards simulation and modeling, but something that's always been the thing that really got me excited about computing and programming in general was always the concept of artificial intelligence. And I'm joined here with my colleague, Luke. You want to go ahead and introduce yourself?
Sure, I'm Luke Wilson. I work at Dell as well as at Visius. Been doing AI since before you could call it that. At least the last time you couldn't call it that. It goes through waves, so you find that people say they work in AI until it's not cool anymore, and then they call it something else, and then they come back, and then um, you know someone decides, oh, we should stop calling it that again, and so we do. But we've been working in this space for almost 20 years together. John and I first started working together in college about 20 years ago. It's 2003. So it's been a while that we've been doing this, trying to come up with all sorts of different crazy ways to make computers do things that would take far too long if we wrote a traditional algorithm for it. So that's really what we focused on, is making computers do things that look like magic but really aren't.
Yeah, I mean, it's been a journey, and I think that's kind of what we want to dig into today, is more of some of this looks like magic and some of it looks really cool, but a lot of it, when you look, under the hood, it's really just some basic algorithms or some basic functions. But where I think that where this begins is, what really is artificial intelligence and what is just intelligence? Because there's a lot of debate over this right now. I mean, there was recent paper, I think just yesterday, that was, don't call everything AI. I don't know. I think there's a lot to be said about what is intelligence. And I think we need to define that first before we can actually talk about what artificial intelligence is.
Yeah, it's good. It's always good to start a lighthearted evening conversation about technology with a philosophical question. But when people imagine artificial intelligence, they imagine, machines that are, human intelligent. So they have this very homocentric view of intelligence, and I can understand that. I think people want to believe that human intelligence is some sort of great grand thing, and we have great examples of people who have been considered throughout history to be intelligent. There's all sorts of folks. You see Einstein there, you see Stephen Hawking, Isaac Newton's in there, Nikola Tesla, and even Alan Turing up in the corner for the computer people. We consider humans to be intelligent. Now, should we? I don't know. But that's kind of the example we hold up as the definition of intelligent. The problem with the definition of intelligence is it's sort of like the definition of pornography. You know it when you see it, but you don't really have a clear definition. And so we need to first put a definition around intelligence before we can start talking about whether or not artificial intelligence is intelligent in and of itself.
Yeah, I mean, we talk about humans being intelligent, but really these are all just basic tasks, right? If we break it down biologically, we have eyes that can see, they do one task. We have vocal cords, and the brain puts it all together, all these different systems. While we call that intelligence, why can't we just call making a system that can see a picture and identify if it's a cat or a dog? Isn't that intelligence too, because it's actually doing that same sort of concept, right?
Yeah, and we see examples of intelligence all throughout nature. There's these examples. You mentioned the eye, but there's all sorts of different types of behaviors that I personally would consider intelligent, and they're not intelligent in the abstraction, complex, thought-provoking, going to build a PhD dissertation sort of way, but these are intelligent behaviors, and they're made by bringing together a whole lot of separate smaller, less complex behaviors. So they have what's called this emergent property or this emergent behavior, where you see thousands of birds, swarming, flying together, swarming in these fashions. You see reindeer here that are moving together in a geometric pattern. And so these are all examples of what I would call natural or biological intelligence, where you're using the sensory input from the outside world and processing it in an optimized fashion in order to accomplish your goal, whether that's to survive or to find food or to protect. Um, and I think a really interesting example, because there's a lot of these natural phenomena that we copy in computer science in the field of AI, if you want to call it that, that are based on natural phenomenon, these nature-inspired techniques. And flocking and swarming patterns are one of those things we tend to replicate. Another thing we emulate is the immune system. So I worked in artificial immune systems for several years, and it's an interesting metaphor. And that's what all of this is. We use nature as a metaphor for building complex computer algorithms. Uh, the immune system itself is a very interesting system. You wouldn't necessarily think of it as being alive because it's part of you and you're alive, but it's a sort of an intelligent system within an intelligent system. It has the ability to identify whether or not um, other cells are self or non-self. It has the ability to mount an appropriate response. And if it doesn't have the ability to mount the appropriate response, it has the ability to learn what that appropriate response is. And that's all a vaccine is. We're seeing the COVID-19 vaccines begin to roll out across the world. All we're doing is teaching our immune system how to combat this virus. And that's an intelligent system in and of itself. The ability to learn new things, the ability to adapt to the environment, and respond to new stimuli is a hallmark of intelligence.
And I think where you see that the repeated thing in nature, at least, is those systems are all built around one main goal, and that's survival and longevity, right? So these are essentially long optimized evolutionary models, things that have evolved for millions of years to be able to understand how they can adapt to identifying a predator versus a prey, or identifying what is a dangerous situation versus a non-dangerous situation, or like these reindeer identifying a dangerous situation and instinctively protecting the flock. So I think where we're seeing that in nature is all of these are optimizations of survival, right? And I think that's intelligence, isn't it?
Absolutely. Intelligence is just an optimized response to external stimuli in the end. That's really all it is. And we can talk about higher order, abstractions of intelligence. But when you really get down to it, intelligence is just an optimized, it's not optimal. I mean, we never do anything the perfect way, but it's an optimized response to external stimuli. And so I think that's the definition we really need to start using when we think about computer or machine intelligence, when we start trying to decide whether or not something is intelligent. We have these concepts like the Turing test. If a computer can trick a human into thinking it's a human, does that make it intelligent? Um, but there's all sorts of different types of intelligence that we need to be willing to accept as valid before we start talking about recreating that intelligence in machine systems.
So I think where we're landing here is the basic definition, right? Is just the ability to produce an optimized response to an external stimuli. So the environment changes, we can adapt to it, and we can change our result to help, as you said, not optimize, but in an optimal fashion. What do you mean the difference between optimized and optimal?
So let's take an example. So if you were to walk out into the street and then notice a bus heading toward you, um, your reaction to that external stimuli, the visual or auditory knowledge that the bus is coming toward you, would be to jump out of the way. Do you jump out of the way in the most optimal fashion? Probably not. But if you jump out of the way well enough that you don't get hit by the bus, then that's a good enough response. And that's really all that intelligence is this ability to do something in a good enough fashion. But do it in a short enough time that that response is useful. It doesn't help if you decide to jump out of the way of the bus when the bus is already on you.
Right.
You have to have enough time to do that. So it's never going to be an optimal response. Intelligence is not about perfect answers. Intelligence is about good enough answers in a reasonable amount of time.
I like
And those
that.
are the types of computer algorithms we want to build.
Exactly. Exactly. But what about artificial intelligence? So I think we've kind of nailed in on what we think intelligence is, and we can debate that in the Q&A afterward, because I think we're just going to say it's pretty general. Viruses may be considered intelligent. The immune system is intelligent. A herd of deer is intelligent, even if it's not the reindeer by itself being intelligent. What about the artificial side? Where does that come in?
Well, I think if we broaden our definition of intelligence, then we can start to think about an array of different types of artificial intelligence. And then I think the question becomes, is it really artificial? I mean, what are we really doing in a synthetic, computational, or a mechanical system that's significantly different at the most fundamental level from what a biological system would do? And so I think it helps to have kind of that definition, of intelligence being that response to external stimuli as kind of the starting point. In fact, Russell and Norvig, in the seminal book Artificial Intelligence: A Modern Approach, defined AI as designing and building of intelligent agents that receive perceptions from the environment and take actions that affect that environment. It's the same definition. The definition of artificial intelligence is really just the definition of intelligence. So
It
there's
really
not
is.
anything artificial about it. It's just not biological.
Right. I mean, this isn't this isn't a bunch of neurons and internal organs making decisions. These are circuits and programs. Is that it to call it artificial? Is that the only reason it's artificial?
That's really the only reason. I mean, from a definitional perspective, uh, the ability to develop a system in silicon that can handle various different situations with all sorts of responses, whether or not they're optimal, is no different than a biological system that does the same thing. Now, the mechanisms underneath may be different. Your biological system's not doing a bunch of math. It's using chemicals. It's using electrochemical interactions in the brain to do these types of operations, but the result, the end result, is very similar.
Yeah, I think the end result
And
is
that's what we're
still
doing.
this picture. I mean, that's it.
Yeah.
It's a stimuli with a model that generates a response, and that comes back to a very simple equation, right?
This is really all it is. You have a model, and based on the stimuli that's placed into the model, you get a different response. So at a very fundamental level, all of intelligence can be boiled down to that equation right there. Y equals f of x. F is your model, x is your stimuli, y is your response.
So
simple.
everything
We can all go home now. I think we're done.
Yeah, I think that's it. We're done. There's probably more though, but I mean, no, that's it. That's intelligence. It is that simple. It's a simple input, a simple response. Those models, however, are not very simple, are they?
No, I mean, it gets far more complicated than that. And the question is, where do we find f? That's the question. Where is this function coming from? And where this function comes from is this interesting concept called function space. So, I mean, we live in a three-dimensional world, 4 dimensions if you're willing to include time and talk about relativity. But in our everyday experience, we live in 3 dimensions. We have an up, a down, a left, a right, and a forward, and a backward. But in mathematics, we're not necessarily limited to 3 dimensions. We're really able to handle billions, trillions, or more, an infinite number of dimensions. We have the ability to explore a space that is unfathomably large, unfathomably complex, and completely dark. And so what we're doing in AI really is searching for functions. We don't make anything in the field of artificial intelligence. We find things. So we happen to find functions in this infinitely large functional space, which unfortunately I can't represent in a two-dimensional zoom window, but imagine that each of these multi-dimensional spaces in this image is connected at every point to each of these other multi-dimensional spaces. And you'll get a nauseating sense of kind of what it is that we're trying to explore. And we're doing it blind. You can't look at it, you can't see it. But every point in this hyperdimensional space is in itself a function. And you don't see what it is until you put some data through it and look at the result. You can't see any sense of what that function is because it's not clearly expressible in a simple algebraic form.
Yeah, I mean, when we talk about the great historic scientists, I mean, they were seeking an answer to a phenomena that they could experience or see. Gravity, speed of light, right? They're things that they could experience and then come up with a simple equation, E equals mc squared, right? In this sort of huge functional space where you see now is the dawn of the data scientists, right? And really these are people who are domain experts at a certain problem and can look into this sort of, I like the infinite, billions and billions large search space, but they can narrow it down a little bit because they kind of understand their problem and they might know which area to search in first. It's not always just a shot in the dark, right?
Yeah, absolutely. You're gonna find very suboptimal functions at first. You're going to, and that's really all we're doing. I mentioned before that it's an optimized response to stimuli. Every time your brain responds to something, it's in a sort of mathematical sense executing a function, and then that response is either good enough or it needs improvement, and maybe you learn something from it. And what is that learning actually doing? When you're learning something, when you're training yourself, what you're doing is you're changing the function, you're changing that model inside your brain. Your brain is searching for a new function that is going to more optimally respond to that stimuli next time it experiences that stimuli. So so when we're looking at this space, every data point we pass through gives us some sort of indication of, based on the response that's given, we can compare whether or not we think that's a good enough answer, and then we can go back and look further through function space. And that's where these different types of these different techniques that we use in data science and machine learning and deep learning, this is where they all come into play. Because if you think about it, if we look at the different statistical models that we use in machine learning, like regression and clustering and support vector machines and whatnot, these are different ways to search the function space. They search in different sub areas of function space with different levels of dimensionality, and they're tasked with using the data that they have, and whether or not they have labeled data or not, depending on whether it's a supervised or an unsupervised algorithm. Supervised algorithms, they're going to use labeled data to help them make that optimization decision. Unsupervised algorithms are not. They're just going to use examples from the other data that exists in that they're looking at, but they're looking for different functions. They're searching in the general vicinity of the function that they use to evaluate the first data point to figure out if they can find a function that's going to better evaluate the second data point. And so this process of searching through function space can take all of these different types of approaches. We're very good with mathematical approaches. We have hundreds of years of experience using mathematics to do this exploration. And so we have very tried and true statistical methods like regression and classifiers and random forest as great ways of searching lower dimensional function space to find great answers to the types of to certain problems. You wouldn't want to use a higher order sort of search operation in order to solve a problem that you can adequately solve with a lower dimensional solution. Just
No, and
like
that's
just like with the laws of physics. The laws of physics exist in 3 dimensions, 4 dimensions if you add time. Why do you need more dimensions? They completely and correctly describe the world in which we live. So there's no need to add extra dimensionality.
right. You don't need extra dimensionality to get the results. And well, these are tried and true methods that have been used in research and business because they didn't need a whole lot of compute power either. These are already optimized to run. You pencil and paper a lot of this stuff if you have the time, but you can run all of these regressions and clustering and random forest on a laptop today. These are didn't require the computational resource, one, because they're not searching as large of a multidimensional space most of the time, right?
Mhm.
But they didn't have to. I think that's the point, right? They were already optimal for their targets.
Right. If it ain't broke, don't fix it. So don't, if you're working with data that is only has a handful of dimensions, or you have a very strong mathematical correlation between your independent and dependent variables, you don't need to go to a higher order search operation. Why am I going to use a neural network, for example, if I want to use an example of one of the most extreme search tools I can use for function space? Why am I going to use a neural network to solve a problem that I can solve with linear regression? If I just want to figure out if there's a correlation between zip codes and house prices, I don't need to use a neural network for that. I can use regression, and that's
Right.
just fine. And so, there's no reason to bring, there's no reason to bring a grenade launcher to a knife fight. In this case, you just want to use the tool that's going to do the job you needed to do.
And like I said, those tools did the job for a long time, but
Mhm.
there's something that's happened really recently in computing. I mean, within the last 5 to 10 years, I'd say, maybe 5 years, really. For the longest time, Luke and I mentioned that, we actually started doing things like this about 20 years ago, doing genetic algorithms. Again, not AI back then. It was graph and it was search. It was things that were important. But the other piece that we're really able to do now is search these massive function spaces with artificial neural networks. And this is more of the deep learning side of artificial intelligence, if we have to label it.
Yeah, so we have all of these different tools. We have the statistical models that we've looked at. We have the laws, the algebraic rules that we can apply to certain things that work great in they find they find models, they find functions that work really well in the lower order spaces. Um, but are you going to build a regression that can tell if a picture is a cat, a dog, or a sandwich? Probably not. Are you going to build a decision tree for that? Probably not. So when we need to go to these more complex, more abstract concepts, you know, trying to decide what something is, trying to identify something, or even do something like interpret audio and give a vocal response. These types of things are very high order functions. And so you need a much higher order search tool to search function space for functions that work for these types of problems. And so we go back to nature, right? We have to go back to nature and find a metaphor, find an analog that allows us to look in these really high order spaces. And we know of one. We have one example in nature that does extremely high order reasoning, and that's the brain. The human brain is the only example we have. Um, so why not replicate it? Why not mimic it? And so we're looking at an example here. So you see a real picture of of neurons, in a tinted frame there, and then this little animation of the asynchronous properties of biological neural networks. How do we bring some of that capability to bear in a computational sense? Well, we can do it with artificial neural networks. So you see a simple example here. In this case, the stimuli is an image of a dog, and it passes through a few layers and it produces the output dog. And what happens in this process is that at every level, at every neuron, every one of those circles you see there, that there are a few things that happen, very simple mathematical operations. Every input is multiplied by a weight factor. They're all summed together. They may be added to a bias. So you have a very simple, mx plus b sort of mathematical operation going on at the input layer, and then you add an activation function, which is normally nonlinear. So you want an activation function that sometimes fires, sometimes doesn't, has a little bit of irregularity in it, so that you can handle the nonlinearity of the world that you want to interact with. And these simple operations, when you couple them together into very large neural networks, create this type of emergent behavior that we're searching for, this ability to approximate very high order functions using very simple mathematics.
And this is, an oversimplification of that network, but the work that goes into this is, thousands of pictures of cats and dogs and hundreds of thousands of pictures of not cat and not dog, so that we can actually train these models to really figure out what it's supposed to see. I mean, we can't just give it, unfortunately, we can't teach it like a human child, where you can say, here's a dog, and they see one dog and they know what a dog looks like from now on. These systems, you have to really tweak all of those little the neuron pieces to make sure that they're firing in the correct way, because they're each doing different things. In computer vision, like this, when we're trying to look at pictures and identify things, we use convolutional neural networks a lot. And as Luke was talking, it's a lot of layers here of really not complex mathematics, but a lot of it. And as it's going through these layers to continue to train this model, we have to continuously feed it new data and continuously feed it bad data, and then continuously test it and say, does that look like the result I want it to? And if it does, let's move on. And if it doesn't, let's shuffle it up a little bit and see if we can fix that. And that's kind of in the where I like to look as the sort of that magic space of AI is we have these very rigid concepts of how to build these layers. But then sometimes after we're done building the models, we can just start pulling layers out, and the models still produce really great results.
Yeah, and the thing about each of these layers, so if we think about each neuron in a neural network, each one of them has different parameters. It has different weights you can apply to each input. There's different biases. There's different activation functions. There's all sorts of different parameters that you can tune in a neural network. And each of those parameters essentially corresponds to a dimension in function space. If you want to, kind of grossly simplify it. And so we were building neural networks now that have millions, billions, and trillions of parameters. So they're exploring millions and billions and trillions of dimensions of function space. And so this wouldn't be possible without looking back to nature as an inspiration. And with vision, it's even more important, because when we think about it, how do we know that a dog is a dog? Well, it's got ears that look like this, and it's got a snout that looks like that. And so when we construct a construct, an internal abstraction of a dog, we're using these abstract concepts. And neural networks can do something very similar by taking greater and greater levels of abstraction at various layers inside the network. And they're doing that based on another nature-inspired analog, and that's the eye. So if you think about it, the brain itself comes all the way out to the front of your face where the eye is located. The eye and the brain are intimately connected to one another, and there's an enormous amount of processing that occurs in the eye before any of that data is actually sent to the brain. And convolution is another way of mimicking a lot of that process. We see it in the retina of the human eye, a whole series of cells that do processing kind of post photon impact. You have these photon receptors on the back of the retina, and then there's the electrical signals that are uh, merged and mashed and swizzled, and there's these connections that occur between all the different layers of cells in the retina before any of that data is ever passed on to the optic nerve and then sent to the brain for further processing. So you have this enormous amount of processing on the edge, um, that occurs before you get back to the core data center in the middle of your skull. And and so we want to be able to replicate that kind of capability by doing a lot of these abstractions through convolution that would normally happen in the eye.
Yeah, I mean, it continues to show that nature is always a really great way to look when you don't have any other options. If you've explored all of the known mathematical and physical properties that you can come up with, and it's still a brute force calculation or a problem that just can't be solved by a computer, this is when we go and look at nature. And we say, well, what did evolution do over time? How did, and that makes that creates an easier search for that huge search space. We can start to narrow in on certain areas that we think will be successful.
Well, why
Beyond
wouldn't we take
just,
advantage of 4 billion years of trial and error? I mean,
yeah,
it took 4 billion years of life on Earth to get to this point. And evolution is not a linear sort of thing. It is not recursively progressive. It walks around sort of randomly, but there have been an enormous number of biological optimizations we can take advantage of. Why would we want to learn all that from scratch?
yeah, and I mean, we've started to apply that same concept to other work that we've done in our lab. Um, you know, being able to identify cats and dogs and sandwiches from images is very cool. But doing important things is a little more interesting. And so we want to talk about some more ways that we can dig into deep learning with a couple of different techniques. So our group did a little project with a model called ChexNet, which was to take a look at chest x-rays and identify a handful of different pathologies, pneumonia and tumors and things like this. Um, what we found though was that there was a really great method, and this is a tried and true method again that we have in nature all the time, called transfer learning. We're able to take models that have already been created. In this case, the classic, it's called ImageNet, or we like to call it the cat dog sandwich model, and it has tons of photos, and it's a well-known data set in the that's out in the wild that people have trained, and you can get all sorts of stats on it. But it's really good at identifying cat, dog, and sandwich. Well, what we wanted to do was say, can we take that work that's already been learned about identifying edges and identifying different gradients and identifying all those sorts of things to know what's cat, dog, and sandwich, and can we apply that to a different problem? Can we just can we start to take that same model and feed it all of these chest x-rays and test it from there? And what we find is that we can reduce our overall computation time. One, I think we're again reducing that function space we have to search in because we've kind of already done that work up front. And that again allows us to kickstart our work right away and say, well, we've already learned something. Let's move on from there.
Yeah, I mean, instead of starting from a random point in the dark, if you have a reasonable starting position, even if it's not in what you would believe is the same domain, in this case, identifying whether or not something is a dog sandwich or car is not the same as identifying whether or not a patient has pneumonia. But it's in the same region of function space. So you can transfer this knowledge. You can start with some or all of the neural network um, trained to do your cat dog sandwich identification, and then add on to it, or augment it in just a little bit, and then search in the region around that initial function to find a function that works really well for identifying pneumonia and emphysema, identifying cancer. We took the same model. We started with cat dog sandwich, we transferred it into chest x-rays, and then we transferred it into mammograms. So you can keep transferring these lessons around because you're taking advantage of this localization property inside of function space. That all of the functions for these types of operations all exist in the same part of this construct. So you can just start with something that looks very dissimilar and say, well, at least it's a vision problem. Let me start there, and then more easily find the answer you're looking for with less training time, less computation time, less effort.
Yeah, and all that, less computation, less effort. That's all, less energy that's spent in retraining models. That's how much faster you can start, because we can always build off of what's already begun. And another thing about this, for chest X-rays, for mammograms. I mean, I think you nailed on a couple of the words there. Is augmenting, and it's to augment our already known things, right? These are chest X-rays that have been annotated by well-trained radiologists, and the concept is, of course, not to replace a radiologist, but the true problem of scale today is we can't train enough radiologists to be at every hospital in every part of the world, but we can train a system and copy that and put that all around the world at virtually zero cost, right? Once it's already made. That's a lot of power that you're now putting into people's hands. And I think that's pretty cool. And one of the really neat things that you can continue to do with some of these AI models.
Yeah, it's one of the real advantages of machine intelligence versus biological intelligence. You can't just take your local radiologist and make a copy of them and have two of them, reducing, doubling the amount of knowledge you have. You can't spread them around. But you can take a machine intelligence model and you can copy it exactly. And you can copy it 1,000,000 times in exactly the same way. And it will have that same function. That same model is able to be applied in hospitals, in personal, in small scale machines, in the richest country, in the poorest country, anywhere you need it. And it costs you nearly nothing to make a copy, just a few electrons worth of electricity.
Yeah, transfer learning, that's a huge win in AI, and it's going to continue to push us forward. We actually did there were some bits of transfer learning in here as well as a few different models. And this is where we start to get a lot bigger. This isn't just a simple system like we showed earlier. That's hey, is this a cat dog sandwich, or what's in this chest X-ray? But this is being able to combine a lot of different concepts. We've all lived through the telephone trees, listening to really robotic sounding voices that are just pre-recorded phonemes. Nobody likes talking to a robot on the phone. But bigger than talking to a robot on the phone, we've already seen systems that can automatically take in your voice and closed caption it, right? Like you can do that right in Zoom. You can also translate text to text from language to language, like English to Spanish or German to English, and even programming languages, C to Java. But the next step was a little bit harder. Well, now that you've been able to translate a voice and say, I want to be able to speak to my friend in Germany, and I want to talk to him in his native tongue, and I want him to reply and hear him in his voice in English. This would be a really great tool for the world, but we're missing that last step of that, how to make that human sounding voice. And so this was a project we worked on, and the goal here was to see how quickly we could train a new voice. And it was pretty neat because we were able to really I think we got the time down to something like 40 hours to train this model. But it's with a huge amount of data, right? I mean, I think it was 24 hours of recorded voice clips with transcripts.
It's 24 hours of voice clips and transcripts. And yeah, it was about 40 to 41 hours of training time. And the amazing thing about it, and we're gonna play an audio clip for you here in a second, but the amazing thing about this is this audio clip is going through time, through the training process. As as this neural network is looking around in function space, trying to find that optimized function for converting text into voice, um, it goes through this process that sounds very similar to the way children learn to speak. And so you'll hear it at different stages in the search phase, and you'll hear, this kind of random babble white noise, this translation into more specific babbling, more specific spacing of syllables and words, and then all of a sudden, the ability to start emitting a few words and then putting entire sentences together. And so it's amazing how similar this artificial neural network, this metaphor that we use, um, based on the human brain to search this complex space, is essentially doing the exact same thing as a biological brain, as a human brain. Only instead of taking 4, 5, 6 years to learn how to speak, it's doing it in about 41 hours.
Yeah, I mean, I think that's kind of the cool part there is it's like, well, let's do accelerated speech learning. And it also ended up being a really neat way to visualize the neural network in its states as it's being trained. That's something that's always been, it kind of irks a lot of people that they can't get a deep view of what these neural networks, how they evolve over the time of creation. So it was kind of neat to like take those snapshots along the training way and say, well, what does it sound like when it first gets started versus halfway through versus all the way to the end? And so let's take a listen to that real quick.
In fact, anywho, the 38 King. Hello, world. This is my voices. Hello, world. This is my voice. Hello, world. This is my voice.
You can see at the end there, if you've ever seen a normal waveform of somebody talking, it's all of a sudden starts to look like a very natural human wave voice. But it takes it, I mean, it is painful to listen to that first one. That is just jumbled garbage, right? That's random search space. And that's exactly what that looks like. We're in this function space, but we have no idea what we're really looking at.
Yeah, you start with this completely random initialization. You might luck into getting something really close in the first random initialization, but normally you don't. You're in this very weird space where you produce nothing but white noise. But this ability for a neural network of reasonable complexity. This is not a small neural network by any stretch, but it's not one of the enormous ones that we see today coming out of groups like OpenAI. Um, able to take just a little bit of input, just the text from the voice actor and the voice clips, and using that audio, react and optimize the function that it's using, find a new function that's in a more optimal location in function space to produce complete audio. These are not stitched together phonemes or anything like that. If you ever listen to a call tree, you've heard these call systems that have these phonemes stitched together where they just have like the different sounds glued together and they sound very unnatural. This is all synthetically generated. This is the computer's voice emulating a voice actor. Now, in this case, is one voice actor, but there's nothing preventing you from using multiple voice actors in the training process to find a function that is kind of a mixture between all the different voice actor examples that are in the training data set. So So there's an enormous amount of possibility with these types of neural networks, this ability to look deep into high order function space and find the types of models, the types of functions that were before now reserved only for the human mind.
And I mean, we're exploiting it in more than just voice, right? Now we've got photos, still imagery. You can just think about it. I don't have a poll or anything, but just take a look at these images and think about which one is a real photograph versus AI generated. Give you a second to look at it. You know, there's tricks you can usually look for, but in this one, they're both fake. They're both generated using what's called a GAN. And this was some work that we saw out of the NVIDIA research team with a software called StyleGAN. You can get this on GitHub and actually generate your own faces. And this is kind of an interesting world of AI, because now we're starting to think about, when we talk about intelligence, and we said, well, intelligence is just being able to respond correctly, but others will argue that, oh, intelligence is creativity. And I don't know, I take a look at this and this kind of looks like a creative model. What do you think, Luke?
It's a very creative process, and it's another example of where we're using nature as a metaphor, as an example, because these GANs, GAN is short for generative adversarial network, actually consist of two different neural networks, both training at the same time. One of them is trying to decide whether or not the photograph is fake or real, and the other is trying to trick that model by giving it fake images. And so through this co-opetition that occurs inside the GAN training process, both of these functions are being optimized to the point where, as the discriminator, as the critic, learns how to better identify between real and fake, the producer is able to generate more and more realistic artificial images. And so you end up in this situation where you've found a function in function space where you can generate completely synthetic images of people, images of artwork, in the same way that humans do. And if we're looking at neural networks as an analog, as a metaphor for biological neural networks, why is it not possible for a computer to find that function in function space that allows it to be creative in a particular domain, just like a biological neural network? One of us can be creative in a particular domain. I mean, at a fundamental level, I don't think there's any difference.
I agree. And it keeps going further than this, right? We're generating voices, we're generating images, and now, if you've seen the MyHeritage site, they're able to take images and animate them. So taking still imagery, these are my great-grandparents that I've never met, and got to bring them to life. And this is where we start to see this crossover of, I don't know, we always like to talk about what's creepy cool or creepy weird, but this is in the realm of really interesting. Now, being able to bring historical figures to life, or as Luke and I have talked about, what about being able to bring historical figures to life with their own voices?
We've seen a lot of research trying to use AI, trying to generate these high order functions that can take in an image of a person and infer what their voice sounded like, emit as a response a voice pattern, so that it can be used to generate their voice. And so when we start putting all of these pieces together, the ability to generate images, the ability to animate images, the ability to use images to infer what their voice sounded like, and then the ability to create voice from text, we have the ability to bring it all together and bring the dead to life in a sort of digital way. And this was 100% the purview of the human mind up until a few years ago. And now it is possible on a computer. So we're really trying to stretch not only the definition of computability, what it means to be something you can use a computer to do, but the definition of intelligence. What does it mean to be intelligent? And is this still artificial, or is it an actual intelligence?
I think we'll keep debating about whether it's artificial or real, but it is getting weird. Uh, things like just being able to do simple face swaps were the thing of, you had to be a skilled Photoshop user to be able to patch in somebody's face. Now you can download an app and do this real quick. Now we're seeing really weird crossovers like Home Stallone, um, or Arnold in any of your favorite movies, or I really love Paul Rudd on Jimmy Fallon, because I can't really tell if they're different people now. Um, this is creating a really strange environment, I'll say. There's a lot of cool things we can do with this that are for fun and for entertainment, generating new people and images, generating fake actors, generating fake voices, generating whole film and content in on a desktop tower in your house with no director, film crew, or anything ever needed. This is kind of where we look to how AI is radically changing the things that we do today, because it's bringing technology to people that don't need to understand all of the intricacies of how hard it was to do a face swap. It's just, here, just click these two faces and move them back and forth.
And that's the great thing about this process is, artificial intelligence or intelligence systems researchers have been trying to push the boundaries for 60 years now. We've been trying to, create more intelligent systems in machines. And what we've gotten to now is this inflection point where some of that stuff is becoming extremely useful. We have the ability to use neural networks to do, media and entertainment sort of operations, and image classification, things like that. We're starting to see real business applications, real useful societal applications to this technology in a way we never have before. We're also able to do really fun things like replace every single person in the Full House credit video with Nick Offerman. So enjoy and be terrified for a brief moment.
I had to make sure that it was lighthearted as you were talking about the tried and true, the tough parts about AI. And there's a lot of things to consider about AI beyond the fun and creepy cool kind of stuff like this. Now, this is a model that anybody could make their whole family look like Nick Offerman. I mean, and who wouldn't want that, right? So yeah, you can check that out. It's on YouTube. So, okay, a lot of fun and weird things there, right? We're generating voices, we're generating computerized voices, we're generating faces, we're generating animations from those faces. But there's also a huge movement in these massive models that are being generated by the folks like OpenAI. Recently, GPT-3 was released. There's something like 300 apps that are using it, generating over 4.5 billion words a day. How big was that model again, Luke?
So this particular model is a few hundred billion parameters. So it's not the largest model that's ever been, trained, but it is one of the largest, probably the second or third largest model ever put together. So it's enormous in its scale, and we're finally to the point where we're able to produce something that at least feels, from a human perspective, sort of intelligent. We were seeing this really high order function, hundreds of billions of dimensions, and able to do things that are very creative, are very human-like, and are very terrifying. This one model can generate text, can translate, can be paired with these image generation models like DALL-E to do the things that you see here. Take a simple phrase and generate conceptual art based on that phrase. So here you see a couple, there's like, you have snail harps and avocado armchairs. And And this is an amazing ability that, at least until about a year and a half ago, most people would say was squarely in the purview of human intelligence. Is not something that computer or machine intelligence was ready to do. Uh, but but this comes at a cost. I mean, if you think about it, a model like this with a few hundred billion parameters needs an enormous amount of computational power to train. And that's one of the reasons why the artificial intelligence revolution is happening now, is because we now have the compute resources to crunch all these numbers. Uh, but if you think about it, the ability to produce this conceptual art is predicated on the fact that this model required, tens or hundreds of millions of dollars of compute hardware to do it, and required probably millions of dollars worth of electricity.
At least.
And humans can do all of these same sorts of things, but we don't need millions of dollars worth of electricity to operate our brains. I just need an egg McMuffin in the morning and maybe a cup of coffee, and I'm good to go. So, in that sense, we have a long way to go to make, um, this machine intelligence, this artificial intelligence, as robust and capable as biological intelligence, just because the power requirements are so enormous at this point. But it's amazing what can be done given enough compute hardware.
It's amazing what it can be done, but it's also kind of, concerning in a way that even the largest corporations in the world can't do this themselves, right? You have to build an open AI to do that. And then really they're open AI, but they did have to make some money eventually. So
Got to pay for all that electricity.
got to pay for that electricity. That GPT-3 model is not free, but there are folks out there who are, there's another group called GPT Neo that's out on GitHub that's trying to produce an apples to apples version. And, this is a system, like Luke said, that it's able to do a lot of things. You can ask it questions and it will reply most of the time with good answers if you ask it good answers. It only knows what it's been trained on, and it's been trained on the internet and our internet archive of books, right? And there's only so much that we can give to these models for them to learn from. And sometimes you see that does come with consequences in the end, right?
Yeah, it's interesting. This one model, um, does these kind of creative design sorts of scenarios. It generates entire news articles. It can generate all sorts of predictive text. It can do lots of interesting transformations and translations, and it's one model. But they've now built a trillion parameter model that is a model of models. It's a set of models glued together with another model to help it decide which of those other models to activate. Now we're starting to look at building a system that looks very similar to the human brain, which has its own regions of different, interconnected neurons, different models housed within it, with some internal decision systems to help it figure out how to activate those different models.
And this is the cool stuff. Why do we do this? I mean, what is the point of using all this electricity, building all these computers, building all these models, just for robot voices, just for cool avocado armchair art? This is the dawn of the fourth age. This is the new future. This is the fire of our time. Just like the control of fire by early humans was the turning point in technological evolution, humans were no longer afraid of the dark. They had time to sit and think, create language and music, and be creative. This is the same thing. This is the control of data and artificial intelligence. And this is our turning point, when we don't have to think about the mundane tasks anymore, when we can put all that aside and start to really use our brains for what they're great at, and that's being creative and creating new things.
Yeah, I mean, humans are a lazy species by nature. We create tools to get out of doing work. That's how our civilization came about. And so as the tools get more sophisticated, it takes away more and more of the mundane tasks that we had to do before, and gives us the ability to open our minds up to do the higher order things, to do the more abstract things. And so that process continues to repeat. And now we're getting to the point where we're building tools almost as sophisticated as us. Um, But that means that a lot of the intellectual drudgery we have to do goes away, and we can focus on doing the things that even a trillion or 10 trillion or quadrillion or quintillion parameter model could never do. We can go even further. And that is, I think, the real interesting thing is not that AI is going to replace humans. It's not that AI is going to become as capable as humans, because we haven't figured out what the limit is to human intelligence. And every time, something comes along where we say, oh, we can never possibly learn anything else, we learn something else. We learn a new way of doing things. And so that amazing adaptability that we still can't replicate in machines is going to keep us pushing forward and well ahead of the machine systems, the intelligent machine systems that we end up building.
Yeah. I always hate to hear people who are afraid that their job will be replaced by a robot. I mean, I grew up in Detroit, and that was always a thing. Oh no, my factory job will be replaced by a robot. But in a lot of these things, it's not a replacement. It's usually an augmentation, as in making us better in some way. Sometimes it is full replacement, though. I don't believe there will be people driving trucks or trains for very long. There are I don't believe there will be a lot of humans in a warehouse. These are jobs that are, if we can create a machine or a model that can do these things, this should help to elevate the rest of humanity. When we get to the point where we know that we're going to run out of raw acreage to grow enough food for all of humanity, we're already seeing folks turn to growing indoors and using AI to identify the most optimal amounts of water for each plant so that it's the most optimized. And that's where we're getting to, is this AI, artificial intelligence is all about optimizing. Maybe not the most optimized, but optimal. And once we get to more optimized, we keep getting better. And we don't know what our limit is. We haven't seen that yet. So we have no idea how great we could really be.
Yeah, I think that's really the idea is, don't fear, the machine, apocalypse. That's not something that, at least me as a researcher at this point, is remotely concerned about.
Yeah.
I mean, if you're really concerned about it, be sure you don't put your models on the internet. But other than that, be sure to take a look at all sorts of different resources out on the web. There's lots of things you can do. There's meetups, there's all sorts of podcasts. Like Jay mentioned, we have the AI facts, fiction, and fun.
Which should be on this list.
Should be on this list, but we're going to continue making more of those podcasts. So if you want to hear more odd ramblings from the three of us, from myself, John, and Jay, listen to the podcast. We talk about all sorts of things.
But we also always pick another odd person too. So if you're an odd
That's right.
AI expert in the audience and you want to be interviewed on that podcast, let us know.
So I know we talked a lot about software and, philosophical concept of what AI is. If you're a software person, though, you can definitely go check out aiinfrastructure.org and ngc.nvidia. They've got a bunch of containers that you can just run on your system. Everything's already pre-configured. You can do examples and get familiar with building models and doing all sorts of things in TensorFlow and PyTorch. And we know that not everybody's a programmer, as Jay always reminds me. There are a lot of other ways to get involved. Ethics is a huge issue in artificial intelligence. Understanding biases, understanding how AI can be weaponized. What is the liability for self-driving cars going to look like? And what are threats to human dignity that might happen? I mean, it's easy for a programmer or a data scientist to sit in his terminal and drill down on his or her problem. But the reality is there needs to be a larger collective to help understand all of the nuances of how these systems are going to be implemented and how they'll be created. And with that, thank you. And I think we ended right on time.
Great, guys. We have just
the most on time.
We have just a few final slides before we go to Q&A. Very quickly for everybody. Let's put this up here. have some other great events coming up. We hope you'll check these out. This is AI month. We've got AI events next week and the week after. So we hope you'll come back. Next week will be all about real world applications of AI. And then 2 weeks later will be about AI fairness and transparency. Saw several questions in the chat about that. That's going to be the topic 2 weeks from tonight. And then 3 weeks and a day from tonight, we're going to do an AI and whiskey chat where you can come and just ask questions about AI or whiskey at that. And we did that once before in January. I had 30 some people, and it was just a wonderful couple of hours. Stay for as long as you like. We'll put up a web page about it soon. What we don't have on here is that on April 29th, John, Luke, and I are teaching an online AI beginners class. So as long as you are comfortable using your laptop in a web browser, you can take this class and do a little bit of AI by the end of that class. So we'll create a web page for that here over the next few days, but please mark that down. I think it's April 29th from, I believe it's from 11 a.m. to 2 p.m., I think is what we picked. Sort of middle of the day so that people on the West Coast could take it, but not so late that people in Europe couldn't take it. So since we've had all of the above on our event. So we'll post, it's not even on this list, but we'll post it. Then you can see we have some other great events coming up in smart cities, immersive experiences, blockchain, Bitcoin and cryptocurrencies, and later in the year, money and finance, robotics, energy, autonomous vehicles and drones, and more.
So like I said, if you weren't here before, we have a Slack and we would love for you to join. I know for a fact, John's on the Slack. Luke, I think you're on the Slack too.
Yes.
And if not, you will be. Yeah, on the AF Slack. But it's a way to ask questions there, a way to get connected, a way to find out other opportunities. Join us on Slack.
And once again, want to thank these sponsors. I hope you take a look at this list and support these companies. There are some national and global technology giants, including some that are active in the AI space, and some that it's implicit in their name, like Cognitive Scale and Valkyrie Intelligence, but also like AMD and ARM and Dell Technologies. Other companies that are in Austin companies or regional or national companies that just care about the intersection of tech and society.
And I saw some of our Austin Pathways friends. Kate, you can say hi in the chat if you're still on. But it is really important to help others get connected during COVID-19 and beyond. Donate. We invite you to donate your devices to Austin Pathways. So we know that everybody probably has a device you're not using, a computer, a tablet, a smartphone. Please, there are people in Austin right now who could use that to learn and work and be well remotely. So Austin Pathways will pick it up safely from you, refurbish it, and deliver it to the residents. Please, you can call them. We'll send this out. You can also always find it online on our Austin forum, or you can email info@austinpathways.org. And Kate's here too.
I know donated a Dell XPS 15 and Kate herself picked it up. So
That is like a celebrity. This is celebrity spotting as far as I'm concerned.
So thank you all for coming tonight. We're going to have Q&A in just a few minutes. We'll pick questions from there, but you can also ask more during chat. Please share the events, the upcoming events. It's going to be a busy month. We want a great turnout. Every event will be different. So we hope you enjoyed tonight. You'll find very different content at each of the next two and at the AI and Whiskey Chat.
Oh, I'm sorry, I'm trying to make sure if you've asked a question before I answer this question, if you've asked a question, don't go anywhere because we are going to get to the Q&A and there is a winner within the Q&A.
There's a lot of good ones. I don't know how you're going to pick, Jessica.
I don't know. We're going to see. I'm going to have AI pick. I created a little bot that is searching through the questions right now.
Uses GPT-3 to find the best question.
The best question. But we want to hear from you. What is the best thing you learned tonight? You have 30 seconds, share it in chat. There was a lot of great information. So we'd love to hear in chat, what was the most interesting thing to you that you learned? I really loved hearing the language. I love the nature piece because I love nature. And then it was really fascinating to hear the voice learning too. StyleGAN, GPT-3, lots of good answers. Absolutely. I agree with you, Jason, the voice learning. StyleGAN is crazy. Learning is intelligence, not response. AI mimics natural phenomenon. Evolutionary biology major. Gabe, you had some great questions. amazing learn about the actual cost of running some of these algorithms, voice synthesis. So you have, I would say, even 2 minutes. Don't go anywhere. We still got a good group here. Jay's just got to run to the behind his shoulder and go grab his whiskey. But then we're gonna bring some people up to chat with our panelists. So if you put a Q&A, if you put something in the Q&A, we will pick you first potentially to join us on screen. So I'm
glad to see at least Bill is now more comfortable embracing an AI future. If that's the one thing that I could do, that hits it home. It's not scary.
I, for one, welcome our AI overlords.
Exactly.
It's so easy to say. Just
one day you might be on vacation and you won't have to ever go back.
That would be amazing.
You know, unless you want to, of course.
Yeah. But you don't have to. Okay. John, I want to hit you up in the chat to be like, which questions do you like?
There's a lot of them.
Still have to sort through them. I haven't even had a chance to look at them.
I know there's a bunch. I wish I should have put
good
you guys up on Slack so I could find out. I have a favorite, but I have very different favorites than people because I come from a very beginner's mind on this. So it's different. Some good ones are just coming in.
Yeah, there's some really good ones in here. Jessica, I think we can go ahead and start picking.
Thank you.
I know. I feel like Luke wants to talk about meat computers. That's a good question there.
Well, okay. So I was just going to bring him on. He had 2 good questions. I'm going to bring him up. Let's see if I can pull him up real fast. This is my favorite part. Ned, I'm going to see if he can pop up really quickly. It only works if somebody is mindly right. Ned, we were going to bring you online to see if you want to ask. You put 2 good questions in the Q&A, and we just wanted to see if you wanted to ask.
There he is.
The question I put was, if you say that the computers will or the AI will free us from drudgery, and they've been doing that for the last couple of 100 years in the Industrial Revolution, but at the same time, at some point, the silicon computers are there's no physical boundary on how big they can become or how powerful they can become, and so eventually, even these creative things that we are supposedly the best at, what's to stop those silicon-based or what other kind of technological-based brains from also taking those functions over as well?
Well, I don't think there's anything preventing, machine intelligence, if you want to call it silicon intelligence, from getting to those higher and higher order parts of function space that really start to encroach on what the brain can do. I think the limiting factor is, the same limiting factors we've always had in computing, which is size, heat, and power.
Space, power, and cooling.
So I mean, eventually you're going to run out of electricity. Unless I can start powering that AI with a Egg McMuffin, like I power myself, it's going to be hard to keep it competitive. And at that point, if you need that much space to build it, it's not like it's going anywhere, so you know where it's going to be all the time. You can unplug it probably. So.
Well, and I think the hope too is that these, as we're building these, silicon-based systems, that we are already at that. We've hit that wall. We continue to hit that wall over and over of, oh, we built it. It's not big enough. Oh, we built it. It's not big. The world's largest computer in Japan is still not big enough to solve the world's greatest problems. So, eventually we'll get back to redesigning those components in more optimal ways for those specific problems. And I see that as our next evolution right now in computing. And you see it pretty popular in the way the boon of new accelerators, new GPUs that are coming, and you see how things like GPUs have, not only because of Bitcoin mining, but also because of AI, the price has just gone through the roof. They're not available because people are using them. So I think that'll continue. It's going to be a long time though, I think, until we're at that sort of optimal compute equal to our brain compute power, eating an egg sandwich and being able to crunch some numbers or be creative.
I'm going to add one thing to this, Ned. Ned, as you know,
How many
we,
Egg McMuffins it takes to run a can full of qubits.
Ned, one last thing to that is, they both hinted at it, but the human brain is less than 20 watts and the most powerful computer in the world is roughly an order of 1,000,000 times more than that and still can't write a good screenplay or tell a good joke. There are things about the way human intelligence works that while we've modeled these neural networks for deep learning, and I say modeled by being inspired by nature, in no way are they remotely as good or efficient as the biological neural networks in our brains for the breadth of creativity and intelligence. They can be faster and more accurate for certain specific problems, but for breadth of intelligence, they're not even close. And so these binary based neural networks are still missing some fundamental ingredients that would be required. And if we only advance those networks on classical computing architectures, we won't catch up to humans anytime. Our kids won't have to worry about it, right? Now, there will be biological computing and quantum computing and some other things that make some huge step forward there, but there are still subtleties about our own neuroscience that we don't understand, so we don't know how to model it. And therefore we can't make an AI that can do it.
I asked Ned, not Ned, I'm going to ask your Colin that I see that if a fake is deep enough and it passes the Turing test, is it fake?
No.
Okay, well, that was good.
We like short answers. That's good.
Okay.
No, I mean, yeah, I mean, if we can, I don't know, if we can fully recreate ourselves, are we still ourselves? Is that now us too? Maybe.
We're only one.
And now we're going to get into the transporter problem in Star Trek and everything. But no.
Yeah. Okay. So next AI event. Okay. Thank you.
Thanks, Ned.
Thank you. Sorry. Now this is where
Thanks,
I
Ned.
juggle. I'm juggling. I am for my next party trick. We had somebody joining in. They said they were from Central America, from Guatemala. I think Gabe did, but I like Gabe. Gabe, I'm seeing if you can pop up. You
should probably warn people at the beginning that if they submit a question, you're going to put them on.
Nope, you're on camera now.
Failed
Get
to
ready.
remind them of that for the whole pandemic. So
Why start now?
Make sure you're wearing
Why?
a shirt.
Why start now?
he is dressed. That's good.
Hey guys, I'm not from Guatemala. I'm actually from the Bay Area.
Oh,
All right.
there was another Gabe that somebody else was in Guatemala earlier. We might have
I
had.
think you have to kick this Gabe off. He's not.
I know,
Yeah.
man. I'm not from.
Cool.
Hey, okay. I'm from Guatemala. I swear.
I'm totally not making this up because I remember being excited somebody was from Guatemala in the group. But Gabe, I liked your questions regardless, so you're in luck.
Awesome. Well, I was actually looking at my Q&A, but I saw that it just disappeared. But I think my questions were along the line of where, for our evolution, you said it was the fourth age. Are we going to rely on this to take us, I guess, whatever the next level may be?
I think
Wow.
so.
I mean, that's really what defines the human ages, is the sets of technologies that allowed us to really go to the next level. I mean, the ability to use stone tools was a huge change, that allowed us to learn an enormous amount of skills that eventually got us to agriculture, and then all of the skills we learned after the agrarian revolution are what paved the way. All of the mathematics we were able to learn, all of the language, all of the higher order abstractions that we were able to learn about because we didn't have to fight for food anymore, are what allowed the Industrial Revolution to happen. And then that just gave us even more. So this is the same sort of thing. It's just going to open us up to possibilities that we were not aware of before.
I love that. And it's almost, my question is also, who gets access to this, like the community of AI, right?
Yeah.
And how are we going to get people involved in it? I've been to a lot of these, right? I've been to a lot of like seminars and groups, and honestly, I think this is the best one so far. Like the way you guys, you guys got good podcasting chemistry and all that stuff. So I love that.
Good.
Gabe from the Bay Area.
No, hold on. Jessica wanted the Guatemalan game, so
You're a good runner-up, Gabe.
Gabe,
Yeah.
you should attend when we bring back the CRISPR folks. They've spoken in the past, and your answer is AI, how we're going to evolve from now on. The answer is technology going to how we're going to evolve from now on, and will AI be one of those technologies? And that's almost certainly true because there's no reason for natural evolution anymore. We take care of ourselves and let everybody survive. And that's a good thing. That makes us human. But that means we're going to have to be in control of our own evolutionary destiny now. And that will probably be largely CRISPR type things.
And that was a
Yeah.
question. I liked how Gabe said that. Gabe, you mentioned artificial intelligence mimics natural phenomenon. Sorry, guys. I can see everybody's Q&A and I forget that they can't see it after they send it to me. And then I'm like, do you remember what you asked? And it's not a quiz. Does the evolution of the human species rely on the advancement in the AI realm? If we're saying that AI mimics natural phenomenon, so then does our evolution rely on the advancement in the AI realm?
No,
Our
no, it
evolution,
doesn't rely on it.
it's now directed evolution as opposed to environmental evolution. And directed means what we can learn and how we can choose to direct it and manipulate it with tools like CRISPR. But AI is fundamental in understanding how some of the functions work. It's going to take us a while to figure out all the proteomics, the function of enzymes and ribozymes and things like that. So yeah, the AI will play a big role in increasing our understanding, which enables us to use the tools to essentially evolve.
Yeah, interesting.
Awesome.
I mean,
Gabe,
there
are
will
you
always
guys
be
here?
environmental pressure. I mean, there's always going to be environmental pressure on species to evolve. Sometimes it's of a species' own making, which has happened a
Right.
couple of times in human history.
But Luke, it only counts if there's enough environmental pressure to prevent successful procreation and carrying on of those genes. It has to be
Yep.
enough pressure to make survival
That's
less probable. So I'm not sure that we haven't mastered our environment mostly enough for that.
Yeah, that would be, if I recall, a pre-zygotic barrier.
Although
Right?
everybody with Texas genes almost died during the great snowpocalypse in February 2021. So
We were all wearing jeans.
All of them.
Yeah, that's great, guys.
Gabe, are you based in Austin, right? This is now just small talk before I bring on the next person. Are you based in Austin or are you in the Bay Area?
I'm in the Bay Area. I'm in the Bay
How'd
Area.
you hear about
Yeah.
us? Even Raleigh wanted to know. How'd you hear about us?
I join any networking event on Eventbrite just to, learn and figure out. And yeah, this is one of them. I was actually in a healthcare NLP summit today as well.
Oh, very cool. I told John and Luke that they were huge on Eventbrite. That was literally my line before. I was like, you guys are trending.
We're famous on a website.
Yeah.
Well, awesome. Well, thank you so much for joining us. We really appreciate it. We hope.
Yeah, thanks,
Awesome.
Gabe.
Yeah,
Thanks,
thanks,
guys. Have a good one.
You too.
Okay, for joining us. Okay, so now I have one of my favorite questions. And actually, I think, hold on. There is Chris. Again, so sometimes I do message people sometimes, PS, just so you know. And people don't always see my chat because it's in like a flurry of chats.
Yeah.
So sometimes I do try to say, hey, are you around? Can I bring you on camera? Definitely not consistently. Sometimes I just like to pop people on like, Chris, are you around? Because Chris asked one of my other favorite questions.
Yes, I'm here.
Because I love social good also. Do you want to ask your question, Chris? It was specifically around social good, but.
There I am, yes. Let me bring my question. Oh, they've gone away.
I
Chris
can't
looks
hear.
like he's rocking that 480p camera from 1996. Chris,
She deleted her camera.
It was the intriguing applications of AI for societal betterment. If you want to expand on that, Chris, or other thoughts.
Yeah, that was, I actually had a two-part question. Was how can we leverage AI and all of its applications for societal betterment, as well as what is the intriguing intersection of AI and nature? So not only can it benefit society and human beings, but nature and wildlife in particular.
So I think on the societal front, that there's a lot of potential with mechanical automated systems to help even the playing field if we can do it right. Right now, there's a lot of inequality. I mean, it costs so much to generate these models. It costs so much, electricity and equipment and all of that kind of stuff. Data scientist expertise. It's very expensive at the moment, but I think the great thing about everything we've ever seen that's digital, from the second we started digitizing music to videos to documents is digital copies are cheap, they're inexpensive. And so it doesn't take long for things that took a lot of money to make, if they're in a digital form, to be turned into something that has absolutely no cost to acquire. So I think there's the potential there, as we get a little further down the line, for a lot of these capabilities to be accessible to everyone. And when they're accessible to everyone, I think there's the ability for artificial intelligence models and functions to be used to really improve society at the most fundamental level, from being able to eliminate a lot of the not just the working tasks. We talk about eliminating drudgery and those types of things, but also eventually figuring out ways to optimize food production, to optimize water filtration, to make all of these things simpler, easier, cheaper. And when we can bring the economics of those basic requirements for life down to a point where human beings no longer have to compete for the tools for survival, we can start building that more equitable social structure, because people are no longer cast aside because they don't have the means to survive.
Yeah. I mean, and today you see AI being applied to wildlife management, to being able to track herds, being able to we have one of the largest bat cages down in San Marcos, and they use AI to help track movement and how the families collect. And there's a lot of different study that's being applied to those sciences. But I think where Lucas was right is, a lot of what we talk about is doing things more optimally. And if we can do things more optimally, we can make our space more optimal as well. And, hopefully, as, folks are thinking down that ethics side, we're making it more optimal for all of life on our planet, not just one life on our planet.
I'm taking notes because I'm actually leading this discussion with my ESL class on Sunday. So.
Oh, were you the one
Awesome.
who started?
Yeah, that was me.
Shared it with your ESL. Thanks for doing that. That was super awesome.
Yeah, we have
Kung Fu-
from 40 different countries. So I didn't realize that we're doing it for 3 weeks in a row. So I will post the link Sunday for the next 2 sessions also.
Kung Fu AI. Also, we had an event in December. We always do a tech and social good event, which is my favorite one. Yeah. And so Kung Fu, we have recordings on the website. We have a YouTube channel where we keep things. And one of our speakers was the head researcher from Kung Fu AI, who talked about their AI and social good projects a bit too. But that's another interesting company to look into.
We need to get Kung Fu AI on the AI Facts, Fiction, and Fun podcast.
Yeah, it's great.
I don't know if Steve is on this event tonight.
No, I don't see him. Thank you so much, Chris, for being here. Thanks for sharing about it with people around the world. You get extra gold stars.
Thank you.
Fantastic. Jay, how many more questions do I have?
Let's do another question, and then pick a winner. And then if the guys will stay on, we could do a few more after the winner too. I know some people are, we promised people 8 o'clock, so we have to finish by 8 with the answer.
Short question, and I did not prep this person, but if she answers, it's also our celebrity appearance of Kate Crego, because she had some really good questions just pop in, and she can give a quick plug for Austin Pathways if she is around to hear me. Very quick plug. Well, that's why I asked how many questions I have. Kate, you have to do your question very quickly because I just wanted to bring you up just because it's always seeing it. But I love seeing your question, and you can say, go Austin Pathways. So
okay, go Austin Pathways, and thank you for your fantastic donations to help extend the reach of machine learning helpers around the city, who are our residents, who can learn to do that when they have a device. I'm just so curious about context and validation loops. Is there human validation of what AI, let's say, of AI and machine learning? Is there a human validation loop market? And will context-dependent learning slow down, or could that be something that kind of slows down the fourth industrial revolution? In other words, by not having standards in that AI factory around context, could that slow it down?
Yeah, I mean, they're, as models are being developed in, in their own countries, for instance, China just released their own version of GPT-3, and it's obviously very focused on translating Chinese to other languages. GPT-3 also does some language translation, I believe, with Chinese as well. So they're really similar because they're all trying to get to the same goal, I think. But you're right, there will be certain biases that could be taken by different countries, of course. They may train it with different data. Is there a human element right now? It seems like it. I mean, when we build things, we look at them and we go, does this do what we said it would do? Does this really tell me that it's a cat, dog, or a sandwich? Is this, when I look at these images, is it really identifying pneumonia in a chest x-ray? The way that GPT-3 has been released is in a beta, and they only let about 300 different organizations start to use it right now. And if you take a look on the web and just do a search for GPT-3 in the news, there are hundreds of articles by all of these different organizations who have played with it. And you get a very interesting view of what it is. Now, some are really great, like Avocado Armchair and Snail Harp. Others are really highlighting how, racist it can be, or how biased it can be towards women, because it was trained with internet data from Twitter and, from all around the world. So it's interesting. There is that human element right now that's able to poke and prod and talk about it. I think that's helpful. But there's no standards yet, but we are, like I said, I think it's all still trying to get to that same goal.
Yeah, I think there's still a lot of validation that has to happen. When I talk to, in my day job at Dell, when I talk to customers who want to put AI into business practice, I tell them that you have to treat any any machine learning model like an employee. You have to give it an evaluation every once in a while. You have to decide if it's time to retrain that employee or fire that employee. And sometimes the model's not working, you need to fire it. Sometimes it's time to retrain it. Sometimes it's working just fine. So there has to be that validation loop that always exists, just like with human employees.
It's also going to be needed, Kate, every time you're trying to do something that's very subjective from human conditions. If the AI is reading sensor measurements and stuff, it's pretty easy to train it to make certain interpretations and do certain actions. But when it's something very human subjective, then human validation becomes even more important. So since Luke brought up pornography earlier in an example tonight, I had a friend that Google used to pay as a human to decide whether pictures were pornography or not, because you can train an AI to recognize whether people are naked in a picture, but you can't train it to recognize the difference between art and pornography very well. Same with jokes. AIs are terrible at telling jokes. You're going to need human validation. Was that joke funny or not? Apparently nobody's trained Alexa in this, by the way, since the joke of the day is always terrible. So anything that requires some kind of human judgment to score it is going to require human validation of those models in particular, because we don't know how to accurately train the corpus of data in a quantitative way. All right. Thank you, Kate. We got to ask the winning question now.
Well, so the irony
the
is,
winning question's no longer online. Someone else is going to win a South-by badge.
Oh, no.
I know. So I actually just, hold on, I'm moving people around. Oops. I actually was just looking, now.
Should we email the person who was going to win and just let them know that they shouldn't have logged out and that they lost it? No.
No.
Send them a consolation prize. Here's an AI.
Now I'm not.
Take home a copy of Austin Forum, the board game.
Man. Other people will take it. I happen to know. I don't have a second runner up really quickly. So I apologize because now I'm scrolling back through. That's why I just pinged all of you guys on the Slack and I was like, or in the chat. And I was like,
Well, I like one on here, but I don't know if they're still on.
who you want to
Because
tell me who?
because it bleeds over into our other interest area. William Tarpai asked one about AI and smart cities. Is William
No,
Tarpai?
he's off too.
Ooh, William, missed that South by badge.
I know.
Oh, could have talked about smart cities.
Yeah.
I know. I saw that one too. There's a
Oh,
lot
I
of
like
people
the one from Eric Maguina.
off.
These
Also,
patterns in computing are being used to solve in the agriculture market.
also not
um,
here.
Farming
Sorry.
also not here.
Oh,
Allison. I'm sorry, I'm not saying. I'm just saying. I'm like, should I tell you who is on? Yeah. I don't know what to do. This never happened to us before. I don't have it. I'm sorry. Sorry, gentlemen. Does anybody in the of the panelists, do either of you guys have a favorite that you
I'm
want to put in
looking
the
for, there's a bunch of good ones, but I'm looking for my favorite. I wanted to scroll all the way to the bottom.
Okay.
Well, here's a fun one to answer at the end, but it's an easy one. Richard Donovan is from Montana. Is Richard still on?
Let me see. He is.
All right, maybe Richard can ask his final question.
oh, I miss Montana.
The answer's unfortunately easy.
Richard.
Not my favorite answer, but
Yeah, so welcome to Montana. Well, actually, welcome to the Montana offices of the California Institute for Telecommunications and Information Technologies.
oh, Larry Smarr's old institute.
Larry is, I'm in Irvine. Larry was, he just retired. Larry was.
I know. I've known Larry for, well, a few years.
Yeah. To know Larry is to know something. Boy, that's for sure. So my question is our sociological development keeping up with our development of, is our development of sociological intelligence keeping up with our development of artificial intelligence? And I kind of couch this in the relative to a colleague of mine has this notion that the cognitive surplus is made from fossil fuels. That is, the reason we have AI is because we have giant computers, and the reason we have giant computers is that we have been burning fossil fuels for a century, and now we have lots of time to think of clever ways of distinguishing cats from dogs. And so just wondering what your thoughts are on that.
I think human evolution is very slow. And I mean, while we're advancing, we're not advancing nearly as fast as our transistors and model development. I don't think that means it passes us per se, but it helps to elevate us if we can continue to keep up with understanding what we're doing.
I'm going to give a harsher answer than that. We are not evolving our intelligence. Our intelligence is very high, but because we are a good species that takes care of our own and allows people to propagate and protect their offspring so that they can propagate, there's no more survival of the fittest, that the fastest or the strongest or the smartest get away from the saber-toothed tiger or the woolly mammoth or whatever is the problem. So human intelligence is roughly flat. Now, applied human intelligence grows because we build on a body of knowledge that does increase. So the good news is no human has to relearn how to make fire and a wheel and all that stuff. So our ability to educate ourselves and have applied intelligence constantly increases. But as John said, these technology increases are exponential. So at the individual scale, even our implied increase in intelligence cannot keep of a single individual cannot keep pace with the technological advances that we see. Good example, a trivial example, but a good one might have been that Go game, where humans were better than Go for a long time. And now Go crushes all humans, and no human will ever catch up in that again, no matter how much they practice. No human will ever beat an AI Go ever again. So I would say that this, from a human perspective, we're not increasing really, except in applied knowledge and not as fast as technology. In sociological, we're always trailing because we have to share that intelligence with each other and make policies to keep up. So it'll always be trailing, but well, I don't think the gap will grow. I just think that, you know, we're always waiting for our sociological intelligence to keep up and make the new policies we need for the new capabilities that we develop. This is why it's important to vote for people that understand technology implications and that to make sure to talk to people in their offices and help teach them technology implications. It increases, human knowledge increase. The latest estimate was that it's doubling every day or something like that. So no policymaker can keep up with that. It's a collective effort to try to keep up in human policy about technology. This is one of my hot buttons. We're going to cover this later in the Austin Forum in the second half of the year with more quantitative metrics of this. We have Sherry Greenberg from the LBJ School of Public Affairs. I don't know if she's still on, but some other people who track things like this. And we'll cover this very question, Richard, in more quantitative analysis later in the year.
Yeah, it strikes me as an interesting question. I do a fair amount of work in AI myself, mostly in manufacturing. And the question is, as we replace more and more people with robots, I put a comment in the chat that the robots aren't coming for your jobs. Your bosses are coming for your jobs.
Yep.
And the question is, you know, the sociological question becomes, who owns the job? If I'm doing a job and a robot comes in and replaces me, do I get the revenue from that robot or does the boss? And right now, I think the boss does. And I just wonder if we'll ever catch up with that. Although, you know, in fact, this very day, I was working with people from UCI and some other people talking about replacing people with robots. I mean, we have a design project where we're actually replacing people with robots.
So it's a goal we have to get to, and we have to deal with what happens after that as well.
Yeah, but for every job that's been replaced by a robot, there's been a job created for somebody writing software for that robot. So it's more of a job transformation.
Or mechanically modifying that robot.
Yeah, there are specific jobs that have been destroyed by every new technology. But
and if you think about it, you know, if the means of production of a certain product becomes automated to the point where the cost per item is now vastly lower than the current selling price, there's going to be this pressure, this economic pressure, this race to the bottom, as other competitors in this space try and undercut the selling price of that product. So what's going to happen is you're going to have this depressive force where things that used to be very expensive become extremely cheap because the cost to manufacture is going to come down eventually.
Interesting. Thank you.